Welcome. I need you to sit down for this because what I'm about to reveal will fundamentally change how you understand the universe. You've been told your entire life that the speed of light is impossibly fast, that it's the fastest thing that could possibly exist, that nothing can catch it, that it defines the very fabric of reality itself. Well, I'm here to tell you something that will terrify you, confuse you, and ultimately make you see the cosmos in a completely different way. Light is devastatingly, horrifyingly slow, and once you understand why, you'll realize we're trapped, not physically but temporally, imprisoned by the very speed limit of the universe in ways that should make you question everything you think you know about existence itself. Before we go deeper, I need to ask you something. Where are you watching this from right now? What country and what time is it for you? Drop that in the comments below. Also, if this premise alone is blowing your mind, smash that subscribe button because the next 230 minutes are going to systematically dismantle your understanding of reality, and you need to be part of this journey with us. Let's begin. When I say light is slow, you probably think I'm insane. Your instinct is to reject this immediately. Light travels at 299,792 kilometers per second. That's 186,282 miles per second. It's so fast that it circles Earth 7 times in a single second. It's been the universal speed limit since Einstein proved it in 1905 with his theory of special relativity. Nothing can go faster. Nothing should go faster. Light is fast, full stop. Except, let me show you something that will rewire your brain. Imagine you're standing on the surface of the sun. The temperature there is 5,505 degrees Celsius. It's the most hostile environment you could possibly imagine. Now imagine you emit a single photon of light from where you're standing, and you decide that photon needs to reach Saturn. That's 1.4 billion kilometers away. A simple journey across the solar system. How long does it take? 8 minutes and 20 seconds. 8 minutes. That photon, traveling at 299,792 kilometers per second, the fastest thing in the universe, takes more than 8 minutes to reach another planet in our own solar system. Here's where it gets truly terrifying. That same photon from the Sun will take 4.37 years to reach Proxima Centauri, the nearest star to us besides the Sun. 4 years and 4 months. The photon is moving at 299,192 kilometers per second, and it still needs 4 years just to reach the closest star. Think about that for a moment. The fastest possible thing in existence is so slow that it would take more than 4 years to deliver a message to our nearest neighbor. But wait, there's something even more horrifying happening right now at this very second that makes light's slowness absolutely terrifying. Imagine you could send a text message to an alien living on Proxima Centauri b, a potentially habitable exoplanet orbiting that nearby star. You'd hit send. That message, encoded into a beam of light, the fastest messenger possible, would take 4.37 years to reach them. They'd see your text in 4.37 years. If they could respond instantly, their response wouldn't arrive until 8.74 years later. That means a single back-and-forth conversation takes almost 9 years. By the time you get their response, you'll have changed, you'll be older. The world will be different. Relationships will have formed and dissolved. People will have been born and died, and they'll just be saying hi back. This is the cosmic cruelty we live under. The universe has implemented a speed limit so low, so pathetically inadequate for connecting the cosmos, that the very concept of conversation across interstellar distances is a joke. We are isolated from each other not by distance alone, but by the sheer inadequacy of the fastest messenger in existence. Now here's the revelation that should make you uncomfortable. We live in a universe governed by this speed limit, and we're only beginning to understand what that means for us, for life, for intelligence, and for the fundamental structure of reality itself. Before we go further into the terror, we need to understand what we're actually dealing with. Speed isn't an intrinsic property of light that just happens to exist. Speed is a relationship between distance and time. And light's speed represents something far more profound, the maximum rate at which causality can propagate through the universe. In 1865, a Scottish physicist named James Clerk Maxwell unified electricity and magnetism into a single framework called electromagnetism. He derived equations, now called Maxwell's equations, that describe how electric and magnetic fields interact. When he solved these equations, something extraordinary emerged. Electromagnetic waves should travel at approximately 300,000 kilometers per second. When he calculated this number and compared it to the measured speed of light, the match was perfect. Light, Maxwell realized, was not a separate phenomenon. Light was an electromagnetic wave. The speed of light wasn't an arbitrary constant. It was the speed at which all electromagnetic phenomena propagate. And this suggested something even deeper. It might be a fundamental property of space-time itself. For decades, physicists tried to figure out what light was actually moving through. They imagined a medium called the luminiferous ether, a substance that filled all of space, through which light waves rippled like water waves in an ocean. This made intuitive sense. All waves we knew about required a medium. Sound waves need air or water. Water waves need water. So light waves must need something too, right? In 1887, two American physicists named Albert Michelson and Edward Morley conducted an experiment that would shatter this assumption and open the door to understanding just how fundamentally slow light actually is. They built an interferometer, a device that splits a beam of light and sends the two halves in perpendicular directions. If light moved through an ether and Earth was moving through that ether, then one beam would take longer to return than the other, because one would be moving with the ether wind and one against it. The result? No difference. None. The two beams arrived back at exactly the same time. Every single time, the ether didn't exist. Light wasn't moving through anything. The speed of light was the same in all directions, regardless of the observer's motion. This single experiment, this null result, was the crack in physics that would eventually shatter everything we thought we knew about reality. Here's what will blow your mind about this. The speed of light isn't actually about light at all. It's about space and time themselves. Think of it like this. Imagine space and time aren't separate things. Imagine they're woven together into a fabric called space-time. The speed of light is actually the speed at which causality itself propagates through this fabric. It's the maximum speed at which information can travel. It's not that light happens to go that fast. It's that nothing can go faster. Because nothing can transmit information faster than the fabric of reality itself allows. In 1905, a 26-year-old Albert Einstein, working in a Swiss patent office, published a paper on special relativity that reframed everything. He didn't ask, what is light moving through? He asked a different question. What if the speed of light is the same for all observers, no matter how fast they're moving? From this single assumption, this elegant simplicity, everything else followed. Space contracts, time dilates, energy and mass are interchangeable through the equation E equals mc2. And most importantly, the speed of light emerges not as an arbitrary limit, but as a fundamental property of space-time itself. But here's what makes light's slowness truly terrifying. This speed limit doesn't just apply to light. It applies to everything. It applies to information. It applies to causality. It applies to you, to me, to every atom in the universe. Nothing, absolutely nothing, can travel faster than light. Not because of some mechanical constraint, but because doing so would literally break the laws of physics. It would allow effects to precede causes. It would allow you to receive a message before it was sent. It would violate the arrow of time itself. And this brings us to the most profound implication. We live in a universe where the maximum speed at which anything can happen is just 299,192 kilometers per second. We live under a cosmic speed limit that is so slow, so inadequate, that it isolates every single object in the universe from every other object. You right now are causally isolated from distant galaxies. The light from those galaxies takes billions of years to reach you, and in that time, everything about those distant objects changes. When you finally see them, you're not seeing what they are now. You're seeing archaeological records of what they were. You're trapped in a universe that's constantly playing catch-up with itself. Let's pause here because this is a lot, and I want you to really absorb this before we go deeper. Drop a comment. What's the most mind-blowing part of what we've covered so far? And if you haven't subscribed yet, now's the time. Because where we're going, you'll need this channel to make sense of it all. Let me give you some perspective on just how devastating this speed limit actually is. I'm going to compare light's speed to other speeds in the universe, and the realization of how slow it actually is will disturb you more with each comparison. A commercial jet airplane travels at about 900 kilometers per hour. The speed of light is 299,792 kilometers per second. That means light is traveling about 999,188 times faster than a jet airplane. That sounds incredibly fast until you consider this. Even at that incomprehensible speed advantage, light still takes 8 minutes to cross the solar system. A jet airplane would take 37 years just to reach the moon. But let's get more cosmic. The fastest human-made object ever created is the Parker Solar Probe, launched by NASA in 2018. At its closest approach to the Sun, it reaches speeds of 586 kilometers per second. The speed of light is still 501 times faster, yet the Parker Solar Probe, this pinnacle of human engineering, moving at over half a kilometer per second, would still take 7,400 years to reach Proxima Centauri. 7,400 years. That's longer than the entire recorded history of human civilization. And we're talking about one of the closest stars. Here's a metaphor that might help illustrate this. Think of it like this. Imagine you're in a car driving at the maximum possible speed, the speed of light. You point the car toward the nearest star. Even at this maximum speed, the maximum possible speed in the entire universe, you will need to drive for 4.37 years without stopping to reach that star. Now imagine your destination wasn't the nearest star. Imagine your destination was the Andromeda Galaxy, the nearest large galaxy to us. Even at the speed of light, the fastest speed possible in existence, your journey would take 2.5 million years. 2.5 million years. The entire evolution of humans, from our earliest ancestors to this very moment, has only spanned about 6 million years. The speed of light is so slow that it would take longer than the entire evolutionary history of our species just to reach the next galaxy. This is what I mean when I say light is devastatingly slow. It's not slow in any absolute sense. It's slow in the context of the vast distances of the universe. And because of that contrast, because the universe is so unimaginably large and light is so comparatively inadequate, we're trapped. Every single living thing, every conscious observer in the universe is imprisoned by this speed limit in a way that should terrify you. Let me introduce you to someone who first helped us understand the implications. Emile Zola wasn't a physicist, but in the late 1800s, a polymath physicist named Hermann von Helmholtz did something remarkable. He considered what the implications of a finite speed of light might be for causality and the universe. But it wasn't until Einstein that we truly grasped the implications. Einstein's colleague, Hendrik Lorentz, derived what became known as the Lorentz transformation, mathematical equations that describe how space and time transform for observers moving at different speeds. These equations proved that the speed of light is invariant. It's the same for all observers. And this single fact, this mathematical certainty, is what imprisons the universe. Here's another mind-blow moment. Right now, at this very second, there are events happening in the universe that you will never know about. There are stars being born, planets forming, civilizations potentially rising and falling, and you will never be able to observe them. Not because of any technological limitation, not because of any limitation in how good our telescopes could be, but because they're happening beyond the light cone of causality. Light from those events will never reach you. The universe is literally preventing you from seeing them. The speed of light creates boundaries in space-time called light cones. Your light cone represents all the events in the universe that can potentially influence you and all the events you can potentially influence. Everything outside your light cone is causally disconnected from you. You're living in an island of causality, surrounded by an ocean of causally inaccessible events. And here's the truly terrifying part. This isn't metaphorical. This is real, this is proven, this is the structure of reality. You are not observing the universe as it is. You are observing a carefully filtered subset of the universe determined by the speed of light. Every single object you see, every single piece of information you receive is delayed. It's ancient. It's a shadow of what was, not what is. Think about it. When you look at the sun, you're not seeing the sun as it is right now. You're seeing the sun as it was 8 minutes ago. The sun could explode into a supernova this very instant, and you wouldn't know for 8 minutes. In fact, the sun couldn't explode because it's a main sequence star and won't explode for billions of years. But the principle remains. You're always 8 minutes behind. When you look at the nearest star, Proxima Centauri, you're not seeing it as it is. You're seeing it as it was 437 years ago. That light left Proxima Centauri when you were a different person, living a different life. And by the time that light reaches your eyes, the star could have changed in profound ways that you'll never know about until 437 years from now. We're all time travelers living in the past, unable to perceive the present, imprisoned by a speed limit that makes the universe fundamentally inaccessible to us. This is the cosmic truth that should reshape your understanding of existence. We need to talk about what happens when things move fast, really fast, close to the speed of light. Because this is where the terror of light's slowness becomes even more profound. It's where we discover that time itself becomes a weapon. Einstein's theory of special relativity revealed something that contradicts every intuition you have about the universe. Time is not absolute. It is not universal. It does not flow at the same rate for everyone. Instead, time is relative. And this relativity gets stronger as you approach the speed of light. Let me give you a concrete example. Imagine you have a spaceship, and you're going to travel to Proxima Centauri, which is 4.37 light years away. For the sake of this thought experiment, imagine you can build a ship that travels at 99.5% the speed of light. That's not physically possible with our current understanding of physics, but let's imagine it. From Earth's perspective, your journey would take 4.38 years. Simple math. 4.37 light years divided by 0.995 c equals 4.38 years. You'd arrive after about 4.38 years of Earth time. But here's what will blow your mind. From your perspective, from the perspective of someone traveling at 99.5% the speed of light, the trip would take only about 6 months. Not 4.38 years. 6 months. This is called time dilation. And it's not a measurement error. It's not a trick of perspective. It's the actual structure of space-time. When you travel at close to light speed, time literally passes slower for you than for people on Earth. This phenomenon was confirmed with incredible precision in 1971 by physicists Joseph Haffel and Richard Keating. They took atomic clocks on board airplanes flying around Earth and compared them to atomic clocks that stayed on the ground. Due to time dilation from the relative motion, the clocks on the airplane actually recorded less time passing than the clocks on the ground. By billionths of a second, yes, but the effect was measurable. The universe was confirming Einstein's prediction. Time is relative, it depends on your motion. But here's where it gets absolutely terrifying. This time dilation means that the speed of light, while being the universal speed limit, has another consequence. It separates causality across time. Think of it like this. If you could travel at the speed of light, time would effectively stop for you. From your perspective, your entire journey, no matter how long it takes in the universe, would feel instantaneous. If you could somehow travel at faster than light, which you can't, this is why the speed of light is not just a speed limit, it's a causality limit. It's the universe's way of ensuring that effects don't precede causes. It's the cosmic law that prevents paradoxes. And it does this by being just fast enough that nothing can exceed it, but not so fast that it trivializes the universe. Here's another mind-blown moment that relates directly to you. Right now, your body is aging at a very specific rate. You're growing older at what you perceive as a normal pace. But if you were traveling on a spacecraft moving at 99.9% the speed of light, you would age much more slowly than people on Earth, by significant amounts. Years could pass on Earth, while only months pass for you. You could travel to the edge of the observable universe and return to find that thousands of years have passed on Earth. You would have aged only marginally, while the entire course of human civilization passed. This is the cosmic cruelty of the speed of light. It's the same speed limit for everyone, but it means that if you want to travel through space, you must sacrifice time. You must experience less of it while Earth moves through more of it. The universe forces you to choose. Travel the cosmos or experience the same timeline as your loved ones. You cannot do both. A physicist named Richard Feynman one of the most brilliant minds of the 20th century, helped us understand the implications of relativity in a deeper way. He developed a framework called the sum of histories, or path integral formulation, which showed that particles and objects don't just travel along a single path through space-time. Instead, they explore all possible paths simultaneously, and the probability of finding them at any location is determined by the interference of all these paths. This is quantum mechanics meeting relativity, and it reveals something shocking. The universe is fundamentally probabilistic. The speed of light is not just a speed limit, it's a probability limit. It determines how fast influence can spread through space-time and how quickly waves of probability can propagate. Let me give you another analog that might help. Think of light speed like the speed of a ripple in a pond. The ripple travels at a specific speed determined by the properties of water. You can make the pond any size you want, but the ripple will always travel at that speed. If you want information to travel across a large pond, you need to wait for the ripple to reach the other side. You can't make the ripple faster without fundamentally changing the properties of water itself. Similarly, the speed of light is determined by the properties of space-time. You can't make it faster without changing the fundamental nature of reality. And since the universe is incomprehensibly large, the speed of light is incomprehensibly slow, relative to the size of the universe. This is why we're trapped, not by any mechanical constraint, but by the very structure of space-time itself. Let's think about what the slowness of light means for the possibility of other life in the universe, because this is where things get truly depressing. The universe is approximately 93 billion light-years in diameter. That's 93 billion light-years. Let me break that down for you. 1 light-year is the distance light travels in 1 year, which is about 9.46 trillion kilometers. So 93 billion light-years is, well, it's a number so large that your brain literally cannot grasp it, and the speed of light is so slow that it would take light itself 93 billion years to cross the entire observable universe. Now consider this. The universe is about 13.8 billion years old. That means the light from the far side of the universe hasn't even reached us yet. We're only seeing the universe as it was 13.8 billion years ago. The universe has existed for less time than it takes light to cross it. This isn't speculation. This is observational fact. Given the vastness of the universe and the slowness of light, what does this mean for other civilizations? What does this mean for contact with extraterrestrial intelligence? Carl Sagan, the renowned astronomer and planetary scientist, spent much of his career thinking about this exact problem. He helped found the Search for Extraterrestrial Intelligence, or SETI, because he believed and mathematically showed that the universe is so vast that it's statistically likely to harbor other intelligent life. He calculated that there could be millions of civilizations in our galaxy alone. Millions. Yet we've never made contact with a single one. We've never even detected a signal from anyone. This paradox is called the Fermi paradox, named after physicist Enrico Fermi, who asked a simple question in 1950. Where is everybody? If the universe is so vast and old and intelligent life is so likely, where are all the aliens? Why haven't we detected them? Why haven't they visited us or contacted us? The answer might be devastatingly simple. The speed of light is too slow. Imagine an alien civilization arose on a planet orbiting Proxima Centauri 100,000 years ago. They developed advanced technology and decided to send us a signal. That signal, traveling at light speed, would take 4.37 years to reach us. We'd receive it in the year 4378,000 AD, assuming our civilization still existed. By then, their civilization would have evolved, changed, possibly disappeared. Any attempt at communication becomes a cosmic joke, exchanging messages across gaps so vast that one meaningful conversation takes longer than our species has existed. But here's what's even more terrifying. Let's say they sent a signal 4.37 years ago. It would just be arriving now. We would finally receive proof of extraterrestrial intelligence. We would respond immediately. That response would take 4.37 years to reach them. So they wouldn't receive our answer until 8.74 years after they sent their original message. By then, 8 years would have passed. Their civilization might have made entirely different decisions. Their political situation could have changed. Wars could have happened, an asteroid could have struck their planet. They could all be dead, and we'd just be saying hello. Now scale this up to intergalactic distances. Andromeda Galaxy, the nearest major galaxy, is 2.5 million light-years away. If an alien civilization from Andromeda sent us a signal tomorrow, we wouldn't receive it for 2.5 million years. That's longer than our entire evolutionary history. That's millions of generations of humans. By the time we received their message, human civilization as we know it would be unrecognizable or gone entirely. This is what I mean by cosmic isolation. The universe is so vast and light is so slow that even receiving a message from another galaxy is practically equivalent to receiving a message from the dead. You're receiving information about civilizations that existed millions of years in the past. You're not communicating with them, you're receiving their archaeological record. This leads to something called the Great Filter. It's a concept in astrobiology that asks this question: if intelligent life is so likely to arise in the universe, why don't we see any evidence of it? Why hasn't any civilization spread across the galaxy, become visible or left detectable signs of their existence? The Great Filter could be in the past, meaning intelligent life is rare and we're lucky to exist. Or it could be in the future, meaning there's some barrier that prevents intelligent civilizations from surviving or expanding. One of the most plausible explanations for the future filter is the speed of light. Think about it. An intelligent civilization that wants to expand across the galaxy faces an impossible choice. Every star system they want to colonize is years, decades, centuries, or millions of years away. Any colony they establish becomes isolated from the homeworld by vast time delays. By the time communication from the homeworld reaches a distant colony, conditions might have changed so dramatically that the message is irrelevant. This creates what's called the causality problem. How can a civilization maintain cohesion and direction when different parts of it are separated by years or centuries of light travel time? How can a galactic empire function when the Emperor's orders take 10,000 years to reach the outer colonies? How can you have a unified culture when cultural evolution happens faster than light can travel between your settlements? The speed of light might be the Great Filter. It might be the reason we don't see advanced civilizations everywhere. It might be why the universe, despite being so vast and old, seems so empty. Intelligent civilizations might be common, but they're all isolated from each other by the cosmic speed limit. They all exist in their own little bubbles, unable to touch, unable to truly communicate, unable to merge into something greater. And if that's true, then we are isolated not by accident, but by the fundamental laws of physics. We are alone because the universe itself is isolating us. Here's where I need you to pause and really think about this. If intelligence is common in the universe, but the speed of light prevents any civilization from ever truly contacting another, then every intelligent being in the cosmos is experiencing the same profound loneliness you're feeling right now when you contemplate this. Every conscious observer, scattered across billions of galaxies, is trapped in their own light cone, unable to reach out, unable to connect, unable to know that others exist. I hope that sits with you uncomfortably, because it should. Let's shift our focus now to what light slowness reveals about the fundamental nature of physics itself, because this is where things get genuinely mind-bending. In 1900, German physicist Max Planck discovered something revolutionary. When he was studying the radiation emitted by heated objects, he found that the energy of that radiation came in discrete packets, which he called quanta. This discovery led to the birth of quantum mechanics, a new framework for understanding the behavior of particles at very small scales. And Planck's constant, the numerical value that defines the size of these quanta, is intimately connected to the speed of light. Here's a profound insight. The Planck length is the smallest meaningful length scale in physics. It's defined using Planck's constant, the speed of light, and Newton's gravitational constant. It equals approximately 1.6 x 10 to 35 meters. To give you perspective, this is to an atom what an atom is to you. If an atom were the size of you, the Planck length would be the size of you compared to the entire observable universe. It's unimaginably small, and the Planck time is the smallest meaningful timescale. The time it takes light to traverse a Planck length. This is about 5.4 x 10 to 44 seconds. This is the smallest unit of time that makes any physical sense. Anything shorter than this, and quantum gravity effects would dominate. And we'd need a theory that unifies quantum mechanics with relativity, something we don't yet fully have. Now here's what's mind-blowing. The universe itself is quantized at the Planck scale. Space-time itself might be granular, discrete, pixelated. Space and time might not be smooth continua. They might be made up of tiny, indivisible units. And the size of those units is determined by the speed of light. Light speed defines the relationship between space and time so fundamentally that it determines the quantum structure of reality itself. Think of it like this. Imagine reality is like a digital image. The pixels are the Planck-size units. The speed of light determines the resolution of this cosmic image. If light were faster, the resolution would be different. Reality itself would be fundamentally different. The speed of light isn't just an arbitrary constant. It's one of the parameters that determines what the universe can be. This connects to something called loop quantum gravity, a theoretical framework developed by physicist Juan Carlo Rovelli and others. In loop quantum gravity, space-time is not continuous. It's woven out of quantum loops, one-dimensional structures forming a quantum network. And the geometry of space emerges from the entanglement of these loops. The speed of light determines how quickly this quantum geometry can evolve. It determines how fast information can propagate through this quantum substrate. Here's another mind-blown moment. Black holes. Black holes are regions of space-time where gravity is so intense that not even light can escape. The boundary of a black hole is called the event horizon, and it represents a kind of cosmic point of no return. But what defines the event horizon? The speed of light. Specifically, it's the radius where the escape velocity equals the speed of light. Below this radius, everything, including light, is trapped. This leads to one of the most profound insights in modern physics, discovered by Stephen Hawking in 1974. Black holes aren't truly black. They emit radiation. Hawking showed that quantum effects near the event horizon of a black hole cause it to gradually lose mass, eventually evaporating completely. This process is called Hawking radiation, and its rate depends on the speed of light. Black holes are slowly dying, and the speed at which they die is determined by the speed of light. But here's where it gets truly terrifying. The speed of light also determines something called the information paradox. When a black hole evaporates, what happens to all the information that fell into it? Is that information destroyed, violating the principle of information conservation in quantum mechanics? Or is it encoded somehow in the Hawking radiation? Physicists have been wrestling with this question for decades. Juan Maldacena and others have proposed that information might be preserved in subtle correlations in the Hawking radiation, but the speed of light plays a crucial role in determining whether this is possible. The speed of light connects to entropy, thermodynamics, and the arrow of time itself. The physicist Ludwig Boltzmann showed that entropy, a measure of disorder, naturally increases over time, which is why we remember the past, but not the future. But why? Why does time have a direction? Part of the answer involves the speed of light and how it constrains causality. An effect can only increase the entropy of the universe if it can causally influence it, and causality propagates at light speed. Think of it like this. Imagine the universe is a cosmic machine, and the speed of light is the speed at which this machine can process information and update itself. If light were slower, the universe would update itself more slowly. Reality would evolve more gradually. Time would feel different. Consciousness itself might feel different. Our brains process information through the motion of electrons and ions, which are constrained by the speed of light. Slow down light speed, and you slow down thought itself. This is why the speed of light is not just a cosmic speed limit. It's the clock speed of the universe. It's the rate at which reality itself can change, and we exist at the mercy of that rate. Now, let's bring this home. Let's talk about what the slowness of light means for you specifically, for your life, for your loved ones, for your sense of purpose and place in the universe. You are made of atoms. These atoms are held together by electromagnetic forces. All electromagnetic phenomena propagate at the speed of light. This means that the force binding your body together is being transmitted at the speed of light. You are held together by signals moving at 299,792 kilometers per second. When you move your hand, your brain sends a signal to your muscles via nerves. This signal travels through electrical impulses, transmitted by ions moving through ion channels at rates determined by the speed of light and the properties of matter. It takes time, milliseconds, but time nonetheless, for your brain to communicate with your body. You are experiencing a measurable delay between your intention to move and your body's response. This is why you cannot have a true simultaneous experience. You cannot be aware of your entire body at once because information about your body's sensations must travel to your brain at finite speeds. Think of it like this. When you touch a hot stove, the pain signal must travel from your fingertip to your spinal cord to your brain. That journey takes time, about 50 milliseconds. By the time you consciously feel the pain, 50 milliseconds have passed. In that time, significant damage could have occurred. Your body has to anticipate this delay and react faster than your conscious awareness. Your reflexes developed to compensate for the fact that consciousness is slow. The slowness of light explains why you cannot perceive the present moment. You can only perceive the past. The light reflecting off this page, these words, takes time to reach your eyes and be processed by your brain. Neuroscience research suggests that by the time you consciously perceive something, it's already about 300 milliseconds in the past. You're always living in a time-delayed version of reality. This has profound implications for your sense of free will. If you're always living in the past, always experiencing delayed information about your own body and the world, can your decisions truly be free? Or are you simply following a script written by your neurons, unaware because the information about your decision hasn't caught up to your consciousness yet? Now scale this up to the cosmic level. You live on Earth. Your loved ones live on Earth. The people you care about most are close enough that light from them reaches you almost instantaneously, in fractions of a second. But imagine your child moved to Proxima Centauri. Imagine they decided to build a new colony on a habitable exoplanet around that star. You'd be separated by 4.37 light years. Could you have a real relationship with them? Could you maintain a genuine connection when every conversation takes nearly 9 years to complete? You'd ask them how they're doing. You'd wait 437 years for an answer. By then, they'd have aged 437 years. You'd have aged 437 years. The context of their life would be completely different from when you asked the question. This is the cosmic tragedy of light's slowness. It doesn't just prevent us from reaching other stars. It prevents us from maintaining relationships across interstellar distances. It limits what family can mean. It limits what connection can mean. Here's something that should truly disturb you. Right now, trillions of photons are streaming from the sun and reaching every surface on Earth. Some of these photons are entering your eyes. These photons left the sun 8 minutes and 20 seconds ago. The photons hitting your eyes at this very second departed the sun when you were doing something different, thinking different thoughts, being a slightly different version of yourself. The past is literally touching you right now. And conversely, photons from your body are streaming off into space at this very second. If an alien were watching you from Proxima Centauri with a powerful enough telescope, they wouldn't be seeing you as you are now. They'd be seeing you as you were 437 years ago. Your youth, your past iterations, a version of you that no longer exists. You are broadcasting your past self to the cosmos. Think of it like this. You're a time-traveling transmitter. Every moment of your life is being encoded in photons and scattered across the universe. Distant observers are watching recordings of your past, unable to see your present, unable to connect with the real-time version of you. To the cosmos, you are always deceased by the time you're observed. You're a ghost in someone else's light cone. Here's a mind-blowing moment that should reframe everything. You have never seen anything in real time. You've never perceived the present. Everything you see is in the past. The light from this screen took time to reach your eyes. The images in your brain are reconstructed from light that traveled through space and time to find you. You are literally living in a museum of the past, and your consciousness is the only exhibit. And here's the final devastation. Due to entropy and the second law of thermodynamics, the past you're seeing is becoming increasingly inaccessible. Old light is getting fainter and redder as the universe expands. Eventually, all the light from distant objects will be too faint and too redshifted for us to detect. Future civilizations will look up at the night sky and see nothing but the ancient light of their own galaxy. They'll have no evidence that other galaxies exist. They'll believe they're alone in a universe empty except for them. We are living in a privileged time, a brief window where the universe is young enough that we can still see its ancient light. But that window is closing. In a few trillion years, the universe will be so expanded that no light from distant galaxies will be detectable. Intelligence arising after that time will never know that the universe is filled with billions of galaxies. They will never know that they're not alone. They'll be trapped in a cosmological darkness caused by the slowness of light and the expansion of space. We are lucky to exist when we do, but our luck is temporary, and the cosmic speed limit is the reason why. Here's something that will make the slowness of light even more terrifying. The universe is expanding, and in some regions, space is expanding so fast that light itself can never reach us from those regions, no matter how long we wait. In 1929, American astronomer Edwin Hubble made a discovery that shattered the belief that the universe was static and unchanging. He observed that light from distant galaxies was redshifted, shifted toward the red end of the spectrum. This redshift indicated that those galaxies were moving away from us. Moreover, the farther the galaxy, the faster it was moving away. The universe was not static, it was expanding. This expansion was initially thought to be slowing down due to gravity. After all, if the Big Bang threw matter outward, gravity should slow it down, like a ball thrown upward slowing as it rises against gravity. But in 1998, two teams of astronomers, led by Saul Perlmutter and Adam Rees, discovered something shocking. The expansion wasn't slowing down, it was accelerating. Distant supernovae were fainter than expected, indicating they were farther away than the deceleration model predicted. The universe was speeding up. This led to the introduction of dark energy, a mysterious force that comprises about 68% of the universe and is driving this accelerating expansion. We don't know what dark energy is. We don't know why it exists, but we know it's there, and it's causing space itself to expand faster and faster. Now here's what's terrifying. Because space is expanding, and because the expansion is accelerating, there are regions of the universe that are receding from us faster than the speed of light. Wait, doesn't this violate what I told you earlier? Nothing can go faster than light? Nothing can travel through space faster than light? That's correct, but space itself can expand faster than light because it's not moving through space. It is space. There's a crucial difference. Think of it like this. Imagine you're standing on a rubber sheet. The sheet is the fabric of space-time. Now imagine the sheet is being stretched. The stretch doesn't move through the sheet. It moves the sheet itself. Distant objects on the sheet can move apart faster than light if the sheet between them is expanding fast enough. This means there are objects whose light is now beyond reach. They're moving away from us so fast, due to the expansion of space, that the light they're emitting today will never reach us. Those objects are beyond what's called the cosmic event horizon. They're essentially causally disconnected from us forever. And here's the truly devastating part. The cosmic event horizon is shrinking. As the universe expands faster and faster, as dark energy accelerates the expansion, the distance to the cosmic event horizon gets smaller. This means we're losing the ability to see more and more of the universe. Regions that we can currently see will eventually recede beyond our reach. Their light will be too redshifted, too faint to detect. They'll disappear from our observable universe. A physicist named Sean Carroll has written extensively about this. He's shown that in the far future, observers won't be able to see beyond their local cosmic neighborhood. They'll look up at the sky and see stars, planets, and nearby galaxies, but everything beyond a certain distance will be invisible. Space will have expanded so much that the light from distant galaxies will never reach them, no matter how long they wait. This is the ultimate consequence of light's slowness combined with the universe's acceleration. We live in a universe with a cosmic horizon, a boundary beyond which nothing can be seen, not because of any physical obstruction, but because space is expanding too fast for light to ever traverse it. Here's a mind-blown moment that should haunt you. We are the privileged observers of a brief cosmic epoch. Right now we can see galaxies billions of light years away. We have evidence of billions of galaxies in the observable universe. But this view is temporary. In a few trillion years, the universe will be so expanded that all those distant galaxies will fade beyond the cosmic event horizon. No light from them will reach us. Future intelligent beings will look up at the sky and see only our local galactic group, the Milky Way and Andromeda and a few nearby dwarf galaxies. They'll have no evidence of the billions of galaxies we know exist. To them, the cosmos will appear nearly empty. This is what the slowness of light combined with cosmic expansion means. The universe is taking away our ability to see it. It's erasing evidence of its own existence. Our observations of the distant universe are not eternal truths available to all future observers. They're ephemeral glimpses available only during a brief window of cosmic time. In some sense, we are the last generation that will ever see the full cosmic picture. All future civilizations will inhabit a darker, smaller, lonelier universe, unable to see beyond their cosmic neighborhood, unable to know the full extent of creation that once was visible. We are cosmic archivists living in a window of opportunity that's rapidly closing. Let's delve into territory that gets genuinely weird. What light slowness means for quantum mechanics, that framework that describes the behavior of particles at subatomic scales. In quantum mechanics, particles exist in what's called a superposition, a state of being multiple things at once, until they're observed or measured. This is the famous paradox of quantum mechanics. A particle can be in two places at once, spinning in two directions at once, having two different properties at once until the moment we try to measure it. Then it collapses into a definite state. This led to something called the measurement problem. How does a particle know it's being observed? How does the act of observation cause a change in the particle's state? In 1935, Erwin Schrödinger proposed a thought experiment called Schrödinger's cat to illustrate the absurdity of applying quantum superposition to macroscopic objects. A cat in a sealed box is both alive and dead until the box is opened and observed. The problem is, this violates our intuition about macroscopic objects. Cats are never both alive and dead. One resolution to this paradox involves the speed of light. When you measure a particle, your measurement apparatus must interact with the particle. This interaction happens through electromagnetic forces, which propagate at light speed. This means there's a fundamental delay between the particle's behavior and your measurement of it. This delay, governed by light speed, prevents you from knowing the particle's state before measuring it. Here's a mind-blowing connection. The speed of light might be what prevents quantum superposition from collapsing into contradiction at macroscopic scales. Because every atom in your body is constantly exchanging photons with its surroundings, constantly being measured by its environment, the superposition is constantly collapsing. You, as a macroscopic object, are prevented from existing in superposition by the relentless interaction with your environment at light speed. This connects to a field of research called quantum decoherence. Physicist Zurek and others have shown that quantum superposition is extremely fragile. The smallest interaction with the environment, the lightest photon, the tiniest disturbance, causes the superposition to collapse into a definite state. Our macroscopic world of solid objects and definite properties exists only because we're constantly being measured by the environment. The speed of light determines how fast this decoherence happens. Now think about this. Your ability to exist as a stable, solid object, to not exist in quantum superposition, depends on you being constantly observed by photons from your environment. You're literally held together by light waves, constantly collapsing your quantum possibilities into the reality you perceive. But here's where it gets even more profound. What happens if you try to go faster than light? What if you could somehow exceed the cosmic speed limit? If you traveled faster than light, you'd be moving faster than light can transmit information about you. You'd be moving faster than causality itself can propagate. This doesn't just break relativity, it breaks quantum mechanics too. It would allow you to see effects before causes. It would allow you to measure something before the measurement photon could reach it. It would collapse the wave function retroactively. You could change the past. This is why the speed of light is so fundamental. It's not just a limit on motion, it's a limit on causality and information. It's the speed at which reality can know about itself. It's the speed at which the universe can process information and update its quantum state. Here's another mind-blowing implication. In quantum mechanics, there's something called quantum entanglement. Two particles can be entangled such that measuring one instantly affects the state of the other, even if they're separated by great distances. This seems to violate the speed of light, but it doesn't, because no usable information travels between the particles. The correlation is established when they're created, and you can't use the measurement results to send information faster than light. But the speed of light still sets the boundary. When you measure one entangled particle, you get a random result. The other particle's measurement result depends on yours in a correlated way, but you don't see that correlation until you compare your measurement results, a comparison that happens at light speed or slower. The speed of light prevents entanglement from being used for faster-than-light communication. This is a recurring theme in physics. The speed of light is not just one constraint among many. It's the fundamental constraint that holds reality together. It prevents paradoxes. It enables quantum mechanics to work. It defines causality. Every mechanism in the universe, from the structure of atoms to the evolution of black holes to the expansion of space, is fundamentally constrained by light speed. Einstein called the speed of light c, and c appears in nearly every fundamental equation in physics. E=mc², the Lorentz factor, the Schwarzschild radius, the equations of quantum field theory. The speed of light is woven into the fabric of every theory. It's not a detail, it's foundational. This means the slowness of light is not a minor limitation. It's not something we might overcome with better technology. It's a fundamental feature of reality. It's as deep as physics goes. Everything eventually decays. Everything eventually spreads out and becomes disorder. This is the second law of thermodynamics, and it's one of the most fundamental truths in physics. And the speed of light plays a crucial role in why this happens. Entropy is the measure of disorder in a system. The second law states that entropy always increases. A hot cup of tea cools down as heat spreads into the surrounding environment. A deck of cards in perfect order will be shuffled into disorder. Stars burn out, civilizations crumble, everything tends toward maximum disorder. Why does this happen? At the microscopic level, particles are jiggling around with thermal energy. There are vastly more disordered configurations of particles than ordered configurations. When particles jiggle randomly, they're far more likely to end up in a disordered state than an ordered state. Over time, everything tends toward disorder because disorder is more probable. But here's what connects to light's slowness. Entropy is an arrow. It points from past to future. This is called the thermodynamic arrow of time. It explains why we remember the past, but not the future. It explains why cause precedes effect. It explains why time has direction. But why does entropy increase in one direction? Why not both directions? Why does the universe show a preference for one direction in time? The answer involves the initial conditions of the universe. The Big Bang happened in a state of extremely low entropy. The early universe was perfectly ordered, incredibly uniform, incredibly organized. From this low entropy beginning, the universe has expanded, cooled, and entropy has increased. We're living in an epoch of low entropy compared to the far future, but high entropy compared to the Big Bang. But here's the crucial point. The speed of light determines how fast entropy can increase in different regions. Heat, disorder, and dissipation propagate through space-time at light speed. The expansion of the universe is also limited by light speed. Gravity propagates at light speed, so the gravity that shapes the universe's expansion can't act faster than light. Think of it like this. The universe is a system evolving toward maximum entropy, heat death where all energy is evenly distributed and no useful work can be done. But the speed at which this can happen is limited by light speed. If light were faster, entropy would increase faster. The universe would reach heat death sooner. If light were slower, entropy would increase slower. The universe would take longer to die. This connects to the work of physicist Roger Penrose, who has proposed something called the whale curvature hypothesis. He suggests that the reason the early universe had such low entropy is because space-time curvature was constrained in a special way at the Big Bang. He's even proposed a cosmological model called conformal cyclic cosmology, in which the universe goes through infinite cycles, each cycle starting with low entropy and ending in heat death. The speed of light plays a role in these cycles, determining how quickly entropy can increase. Here's a mind-blown moment that should terrify you. Every action, every thought, every movement you make generates heat and increases entropy. Your brain requires energy to think. That energy ultimately gets dissipated as heat. Every bit of work you do, every creation, every struggle ultimately generates disorder. You are a localized pocket of order in an ever-increasing sea of disorder. The universe is using you, using all of life, all of civilization, to increase entropy. Life exists because it's a very efficient mechanism for converting low-entropy energy from the sun into high-entropy heat radiated into space. We are entropy-increasing machines, and the speed of light limits how fast this process can happen. It determines the rate at which order breaks down. It determines how long the universe can sustain life before reaching heat death. Now here's something even more disturbing. In the far future, the universe will reach a state called heat death. All energy will be evenly distributed. No stars will shine, no life will exist. All organized structures will have decayed into radiation and particles spread evenly throughout space. This state will be one of maximum entropy, the most disordered, most bland, most featureless state possible. How long until heat death? Estimates vary, but physicists suggest it could take 100 years or longer. That's a 1 followed by 100 zeros. The current age of the universe is about 10 years. Heat death is 90 times farther in the future than we are from the Big Bang. But here's the terrifying implication. The speed of light determines how long it will take for the universe to reach heat death. It determines the rate at which stars burn out, planets decay, and all organized structure collapses into disorder. A slower speed of light would mean the universe reaches heat death even more inevitably. A faster speed of light would mean it reaches heat death sooner. We exist in an infinitesimal window of cosmic time. The universe has been around for 13.8 billion years. It will exist for trillions upon trillions of years more. And in that final, unimaginable future, all evidence of life, all evidence of intelligence, all evidence of anything interesting will have been erased. The universe will be a featureless expanse of radiation and elementary particles, expanding forever, slowly cooling toward absolute zero, completely and utterly dead. The speed of light is the clock that's ticking toward that inevitable death. It's the speed at which the universe is running down. It's one of the parameters that determines how long until everything ends, and we're riding on that clock. Every moment that passes, the universe moves another step closer to heat death. The speed of light ensures that this process happens at exactly the rate it happens, not faster, not slower, just inexorably, inevitably moving toward the end. Let me take you on a tangent that might seem weird, but connects back to everything we've discussed. What if the universe is a simulation? What if reality is a carefully crafted computational universe created by some advanced civilization? This isn't as crazy as it sounds. Physicists like James Gates have found error-correcting codes, the same kinds of codes used in computer programs, embedded in the equations of string theory. Physicist Stephen Wolfram has proposed that the universe might be a computational system, expanding from an initial set of rules and evolving according to those rules, much like a cellular automaton. If the universe is a simulation, what does that tell us about the speed of light? In a computer simulation, there's a processing limit. The simulation can't compute faster than its hardware allows. A simulation running on a supercomputer has a maximum processing speed, and that maximum processing speed would manifest in the simulated universe as a speed limit. The speed of light might be the clock speed of the cosmic computer running this universe. Think about it. If you were designing a universe to simulate, and you wanted to ensure consistency and prevent paradoxes, you'd implement a speed limit for information propagation. You'd set a maximum rate at which causality can spread. That maximum rate would be the speed of light. Here's a mind-blowing implication. The slowness of light might not be a limitation imposed by nature. It might be an intentional design feature implemented to ensure the universe can run efficiently, to ensure the simulation doesn't crash, to ensure that causality remains consistent. This connects to something philosophers call the simulation hypothesis. If advanced civilizations can create simulations of universes, and if the multiverse is infinite, then statistically, it's more likely that we live in a simulation than that we live in the original base reality. The logic is simple. If it's possible to create simulated universes, and countless civilizations do so, then there would be far more simulated universes than base realities. We'd be statistically more likely to be in a simulation. Now, if we are in a simulation, the slowness of light might be evidence of that. It would be the cosmic equivalent of finding a bug in the code. It would be recognizing the speed limit as an artificial constraint necessary to make the simulation run. But here's what's truly disturbing. Whether the universe is a simulation or not, the slowness of light has the same effect. It constrains consciousness. It limits how much of reality any observer can know. It creates isolation. It creates the conditions for loneliness and existential dread. Consciousness awareness emerges from information processing. Your brain is processing information about the world, integrating it, creating a model of reality. That information processing is constrained by the speed of light because all the neural signals in your brain travel through electrical and chemical processes that are fundamentally limited by the speed of light. Think of it like this. Your consciousness is a process that requires information to flow through your brain. That information flow is limited by how fast signals can travel through your neurons, which is limited by the speed of light. Speed up light, and your thoughts could process faster. Slow down light, and your thoughts would process slower. Your consciousness would feel different. You are not separate from the universe's speed limit. You are a direct expression of it. Your ability to think, to feel, to be aware depends on electromagnetic signals traveling through your brain. Those signals travel at speeds determined by the speed of light and the properties of your brain tissue. Here's the truly mind-bending realization. The speed of light isn't just limiting how fast we can travel through space. It's limiting how fast we can think. It's limiting our consciousness itself. You could never think faster than light allows you to think, because your thoughts are implemented through processes that obey light's speed limit. This is why every intelligence in the universe is constrained not just by distance, but by its own cognitive limits. You can't think faster than your brain allows. Your brain can't operate faster than electromagnetic processes allow. Those processes operate at speeds determined by the speed of light. Therefore, your consciousness is inherently limited by the speed of light. We are all, in a very real sense, slow. Not just our bodies, not just our space travel, but our very minds. Our consciousness is a slow phenomenon, constrained by a cosmic speed limit we didn't choose and can't escape. Now that you understand how slow light really is, let me revisit the Fermi paradox with fresh perspective. You remember the question, if the universe is so vast and old, where is everybody? Why haven't we detected alien civilizations? The answer isn't just that light is slow, it's that light's slowness combined with the vast distances and extreme timescales of the universe creates a perfect isolation mechanism. It creates a cosmos where intelligent life, no matter how common, will almost certainly never contact other intelligent life. Think about the timeline of a typical civilization. Let's say intelligent life evolves on a planet. They develop technology over thousands of years. They reach the point where they could detect or attempt to contact other civilizations. How long do they persist in this state? Human civilization has existed for about 10,000 years. Modern science has existed for maybe 500 years. Electronic technology for maybe 150 years. Radio communication, our method of trying to contact aliens, for maybe 100 years. How long will this state persist before something changes? Before we destroy ourselves or transition to a post-biological form or something else entirely happens? Most estimates suggest a technological civilization might exist for tens of thousands to millions of years before encountering extinction or radical transformation. Let's say a civilization persists for 1 million years in a form where they're actively trying to contact others. Now consider, There are an estimated 100 billion stars in our galaxy. If even 1% of them have habitable planets, that's 1 billion habitable planets. If even 1% of those develop intelligent life, that's 10 million civilizations in our galaxy alone. If even 1% of those exist right now, rather than having existed billions of years ago or existing billions of years in the future, that's 100,000 civilizations active in our galaxy at this moment. And yet, we detect none of them. Why? Because the nearest civilization is likely millions of light years away. Light from them would take millions of years to reach us. We'd need that light to arrive during our technological civilization's era. The probability that a civilization's existence overlaps with our ability to detect it is vanishingly small. Here's the math. A civilization exists for maybe 1 million years. The light from that civilization takes millions of years to reach us. These timescales must overlap perfectly for us to detect them. The probability is microscopic. We could be surrounded by active technological civilizations, and we'd never know it, because the light from them wouldn't arrive until long after our civilization ends. This is the cosmic tragedy of light's slowness. The universe could be teeming with life, with intelligence, with civilizations, and they'd all be completely invisible to each other, completely isolated, completely alone. And here's something even more disturbing. The universe might have been far more populated in the past. There might have been a time when intelligent civilizations were common. But as the universe has expanded and cooled, as stars have burned out, as civilizations have risen and fallen, most of that intelligence is now gone. We're looking at ancient light from civilizations that no longer exist. We're reading the archaeological record of a dead universe, unable to know that it was ever alive. The physicist Brandon Carter proposed something called the anthropic principle. It suggests that we can only observe the universe from locations compatible with our existence. This means we observe a universe that appears old, large, and empty because we need an old universe to have developed by the time we appeared. And we need it to be large enough to have produced the heavy elements in our bodies. But applying the anthropic principle to the Fermi paradox leads to a disturbing conclusion. We might be living at the worst possible time to detect other civilizations. We might be living right now in this specific era, specifically because it's an era where intelligent life is rare, isolated, and unable to contact others. The very conditions that allowed us to evolve might be the same conditions that guarantee we'll never meet anyone else. We might be cosmically alone not by accident, but by necessity. We exist because the conditions that allow us to exist also prevent us from contacting others. The isolation is baked into the physics. Okay, let's pause all the cosmic horror for a moment and ask, why does this matter? Why should you care that light is slow and the universe is vast and you'll never contact alien civilizations? Because understanding light's slowness changes how you see your place in existence. It reframes your meaning. It makes you confront the fundamental conditions of being alive in this universe. Here's the truth. You are made of stardust. The atoms in your body were forged in stars billions of years ago. They were scattered when those stars exploded. They fell into a molecular cloud, which collapsed to form our solar system, which gave rise to Earth, which gave rise to life, which gave rise to you. You are the universe becoming conscious of itself. You are a temporary arrangement of matter that has become aware. You are a process, not a thing. And that process is remarkably limited by the cosmic speed limit. Every moment of your life is imprisoned by the speed of light. You can't move through space faster than it allows. You can't transmit information faster than it allows. Your consciousness can't process information faster than it allows. You are constrained, defined, and ultimately limited by this single parameter. But here's the thing that should make you feel empowered. You exist anyway. Despite the constraints, despite the limitations, you became conscious. You developed the ability to understand the universe. You can contemplate your own existence. You can ask profound questions about the cosmos. Think about how unlikely that is. For billions of years, the universe was just radiation and elementary particles. Then atoms formed, then molecules, then cells, then organisms, then animals, then intelligence. Each step was improbable. Each step required countless trillions of interactions, countless quantum events with specific outcomes. countless near misses and fortunate accidents. And yet here you are. Here we are. We exist. We're conscious. We can understand the universe, at least partially. We can contemplate beauty, meaning, morality, existence itself. The speed of light isolates you from the cosmos, but it also concentrates your meaning. You're not lost in a universe filled with countless other conscious beings fighting for significance. You're likely unique. Your specific consciousness, your specific perspective, your specific way of experiencing reality has probably never existed before and will never exist again. This is a profound kind of meaning-making. You are irreplaceable. Your experience is irreplaceable. What you do, how you treat others, what you create, what you contribute, these things matter precisely because the universe is so vast and you are so unique and so alone. The slowness of light gives us a gift hidden underneath its terror. Profound loneliness combined with profound significance. You are alone in ways that can be difficult to accept, but because you're alone, because you're unique, because there's no one else anywhere else in the cosmos experiencing reality, from your specific perspective, what you do matters. It matters absolutely. Think about the people you love. The light reflecting off their faces takes time to reach your eyes. You're always seeing them slightly in the past, but that's okay, because even though you're not seeing them in the present, you're present with them. You can touch them. You can speak to them. You can build a relationship with them right now in this moment without being separated by light travel time. This is the gift of Earth's compactness. This is the gift of living on the same planet as other humans. You can maintain genuine relationships across the distances you navigate. You can be truly present with others. You can experience genuine connection. That's the thing about cosmic constraints. They make local connection more precious. They make relationships with the people around you more valuable. You have access to something that intelligent beings on distant planets could never have. True, real-time relationships with other conscious beings. Use that. Hold on to that. Build your life around that. Create meaning through connection with the people around you, because that's the only kind of meaning that's truly possible given the structure of the universe. And here's something beautiful. Every act of kindness, every moment of love, every creation of beauty, every discovery of truth, these are all rebellion against entropy. These are all temporary victories against disorder. These are ways of building pockets of order and meaning in a universe that's slowly running down toward heat death. You are a candle in the darkness. You burn brightly for your brief time, then you go out. But you helped light other candles while you were here. You helped create meaning. You helped add beauty to a universe that doesn't need it, but is better because you created it. The speed of light is slow. The universe is vast. You are small. But you're not insignificant. You're not meaningless. You're here. You're conscious. You're experiencing the universe. You're part of the story of the cosmos becoming aware of itself. And that's enough. That's beautiful. That's profound. Now, at the end of this journey, I want to bring everything together. I want to show you the final revelation that reframes everything we've discussed and leaves you with a sense of awe rather than just horror. We've established that the universe is vast. Light is slow. We're isolated. Everything tends toward entropy and eventual death. Those are the terrifying truths. But now I want to show you the other side of that coin. The fact that light is slow, the fact that the universe is vast, the fact that we're isolated, these aren't deficiencies. They're features. They're the conditions that make the universe possible in the first place. Think about what the universe would be like if light were faster. If light could travel infinitely fast, then causality would be instantaneous everywhere. A change in one part of the universe would affect all other parts immediately. The universe would be fully connected, fully unified. There would be no space for complexity to develop. There would be no structure, no diversity, no richness. It's the finite speed of light that allows distant parts of the universe to evolve independently. It's light's slowness that allows complexity to emerge from simplicity. It's the cosmic speed limit that makes the universe interesting. Consider gravity. Gravity propagates at light speed. If it propagated faster, stars and planets wouldn't form the way they do. The universe's large-scale structure, galaxies, clusters, filaments, would be completely different. Life might never have emerged. Consider chemistry and biology. Atoms bond through electromagnetic forces, which propagate at light speed. If this were faster, chemical reactions would be different. Atoms might not form the stable configurations they need for complex chemistry. Life might never be possible. Consider consciousness itself. Your brain processes information through electromagnetic signals. If these signals traveled faster, your brain would be fundamentally different. Your consciousness would be fundamentally different. You might not be possible. Here's the mind-bending realization. You exist because light is slow. The speed of light, which we've characterized as a horrifying limitation, is actually a necessary condition for your existence. Without it, you wouldn't be here. Without it, anything like you wouldn't be possible. This is a profound cosmic irony. The very constraint that isolates you from the universe is the same constraint that makes you possible. The speed of light is simultaneously the reason you're alone and the reason you exist at all. Now let's think about time. We characterize time as moving forward, driven by entropy toward inevitable heat death. That's true in a mechanical sense, but from another perspective, time is the medium in which life and consciousness exist. Think about what consciousness requires. It requires continuity. It requires memory. It requires the ability to form patterns and recognize them. All of this requires time. If everything happened instantaneously, consciousness would be impossible. You couldn't think, you couldn't form a memory, you couldn't be. The arrow of time, driven by entropy, is what allows consciousness to exist. It's what allows meaning to exist. It's what allows you to tell a story, your story, from beginning to middle to end. Without time's arrow, there would be no narrative. There would be no drama. There would be no meaning. And entropy, the tendency toward disorder, is what drives evolution and complexity and life. Stars form through entropy, the collapse of disordered gas clouds. Life emerges through entropy, the consumption of low-entropy energy and the production of high-entropy heat. Everything interesting about the universe emerges because of entropy, because of the second law of thermodynamics. Even the ultimate heat death of the universe isn't meaningless. It's the final equilibrium toward which the universe has been working since the Big Bang. It's the inevitable result of the universe's initial conditions. And in some sense, it's beautiful. The universe will eventually reach a state of perfect equilibrium, perfect uniformity, perfect peace. All energy will be evenly distributed. All tensions will be resolved. All disorder will become order, in the sense that perfect disorder is a form of perfect order, complete uniformity. We exist in a brief window between the low entropy of the Big Bang and the high entropy of heat death. We exist in the interesting middle part of the universe's story. And that window, that opportunity, is incredibly rare and incredibly valuable. Here's another revelation. The Fermi paradox might not be a paradox at all. It might be the answer we should expect. Of course, we don't see alien civilizations. They're all isolated by light-speed delays, scattered across billions of light years, their existence windows misaligned across billions of years of cosmic time. The fact that we see nobody is not surprising. It's what physics predicts. But here's what's beautiful about that. It means that every intelligent observer in the universe experiences the same fundamental loneliness we do. Every conscious being faces the same cosmic isolation. Every civilization, no matter how advanced, can only truly connect with others on their own world. Every intelligence reaches out into the darkness and finds only silence. And somehow in that shared loneliness, there's a kind of connection. Not a practical connection, not a way to exchange messages or share technology, but a deeper connection, a recognition of shared fate. Every conscious being in the universe is in the same situation. We're all looking up at the stars. We're all wondering if anyone else is out there. We're all experiencing the terror and beauty of cosmic isolation. Think about that. Right now, on planets orbiting distant stars, and there probably are such planets with life on them, other conscious beings are looking up at their skies. They're seeing light from stars billions of light years away. They're seeing the ancient universe. They're experiencing awe and wonder and loneliness just like we are. We're not truly alone in our loneliness. We're part of a universal experience. Every intelligence in the universe is facing the same cosmic constraints, experiencing the same isolation, contemplating the same mysteries. And here's the final revelation that should make you feel awe. Despite all of this, despite the vast distances, despite the slow speed of light, despite entropy and time and the march toward heat death, life happened. Consciousness happened. Intelligence happened. Beauty emerged from matter. The universe didn't have to create consciousness. The laws of physics don't require it. They would work just fine in a universe with no observers, no one to marvel at the stars. And yet, consciousness happened. Multiple times, probably countless times across the cosmos. Matter organized itself into forms capable of being aware, of understanding, of appreciating the universe's beauty. This is the deepest mystery. Not why we're isolated, not why light is slow. Those are minor physics questions with explanations rooted in the nature of space-time. The deepest mystery is why the universe that follows those laws also produced beings capable of understanding those laws. Why does the universe exist in a state where it can be understood by entities within itself? Why are we here to contemplate it all? That's the truly mind-blowing moment. Not that light is slow, not that we're isolated, but that we exist at all and that we're capable of understanding our own existence. This transforms the meaning of light's slowness. Yes, it isolates us. Yes, it limits us, but it also makes us precious. It makes our consciousness precious. It makes our brief existence in this cosmic moment precious. We're here, against all odds, in a universe that could have easily remained sterile and unconscious. We're here to experience beauty, to create meaning, to love, to understand. That's what the terror of cosmic isolation buys us, profound meaning. We can't reach out to others across the stars, but we can reach out to each other here, now, on this small blue planet. We can build civilizations. We can create art. We can pursue truth. We can love. And in an isolated universe, in a cosmos where consciousness is rare and fragile, these things matter absolutely. They matter more than they would in a universe filled with endless observers. Your choices matter. Your love matters. Your consciousness matters. This is the final transformation. The realization that light's slowness, which seemed to trap us, actually frees us. It frees us from the illusion that we need to be part of some grand cosmic network to have meaning. It shows us that meaning emerges from connection with those nearby. It shows us that consciousness doesn't need to be universal to be valuable. It just needs to be genuine. You are a conscious being in an almost certainly unconscious universe. Your perspective is unique. Your experience is irreplaceable. You are experiencing something that almost no matter in the universe ever gets to experience. Awareness, self-reflection, understanding. Don't take that for granted. Don't waste it. Don't spend your time in an isolated, lonely cosmos pursuing things that don't matter. Pursue connection, pursue understanding, pursue beauty, pursue love, pursue meaning. Because those are the only things that truly matter in a universe governed by a cosmic speed limit that isolates every consciousness in its own little light cone. I want to come back to where we started. I told you that the speed of light is devastatingly, horrifyingly slow. And it is. But now you understand what that means. It means we're isolated. It means we're alone. It means we'll never reach the stars or contact alien civilizations or become a truly cosmic species. But it also means we're special. It means our existence is precious. It means the connections we form with each other right here, right now, on this tiny planet orbiting an average star. Those connections are the most valuable things in existence. The terror is real, the cosmic distance is real, the inevitability of heat death is real, but so is the beauty, so is the wonder, so is the miracle of consciousness emerging from matter. That's the truth about how slow the speed of light really is. It's both the most terrifying thing about the universe and the most beautiful. And once you understand that paradox, you understand something fundamental about existence itself. I hope this journey has changed how you see the cosmos. I hope it's made you feel both humbled by the universe's vastness and empowered by your unique place within it. Remember to drop your location and watch time in the comments. Let me know where you are in this vast cosmos. And please, if this content resonated with you, subscribe, share it with others. Help spread this understanding that we're not separate from the universe. We're part of it, experiencing it, understanding it, appreciating it. We are the universe conscious of itself, looking out at its own vastness, marveling at its own mystery. And that's profound. That's enough. That's everything. Thank you for taking this cosmic journey with me. The universe is waiting for your unique contribution to its ongoing story of becoming conscious.